Hello everyone, I'm Riccardo Cavadini, at the end of my second year of PhD, and I'm gonna talk to you about my PhD research. So starting from some background, we've already talked about the computing continuum today a couple times, but just to give an overview of what it is, it's basically the system that goes from edge devices, from Internet of Things devices, back to edge servers, and then back to edge computing systems, such as virtual machines, function as a services, or HPC centers even. So these are very heterogeneous resources, of course, so we can have CPUs and GPUs, FPGAs, whatever, but also they have different computing capabilities. For example, Internet of Things devices usually have low power consumption, but also low power. As opposed to virtual machines in the cloud that might have much more computing power, but we need to send data back to the cloud, and so we pay that computing power in terms of latency of transmission. So when we have an application, we can execute it on different resources. We can decide where to execute it. But of course, the performance of this application can vary depending on where we execute this application. Okay. So this is the task. It's part of a task that you saw in a talk this morning by Federica Filippini, my colleague, my older colleague. She presented this use case, a bigger use case than this. This is a part of that use case. So basically we have 3 different computational layers. So one is the one made of edge resources, and we call it computational layer 1. Then going to the cloud, we have computational layer 2 and 3 with virtual machines. While then we can have Lambda instances on AWS, for example, and those are function as a services resources. And these at the bottom is our AI application, which, for example, can be an application that needs to record a video of people in a room and see whether or not people are wearing masks. This is from the COVID era, which, of course, is over, fortunately. So this is an AI application divided into 2 steps. Both are deep neural networks. So one is to blur the faces of people in the video, and then the other one is to detect whether or not people are wearing masks. These 2 applications can be mapped on different resources because their requirements in terms of resources are different. And so depending on which resource we map them on, we have different results in terms of latency. So again, for what concerns some little background again, as we discussed this morning, as I was saying, this problem is called resource selection and application component placement, and it's been solved at design time efficiently, very efficiently. In fact, at design time, we have a complete overview of what the computational loads are and what the computational capabilities of each VM is, of each computational layer, let's say. But the thing is that we need to be able to respond to fluctuations that are mostly unforeseeable in real systems. For example, in the demand of a specific AI application component, or in the fact that a VM might not be reachable at a certain point in time for whatever reason. This is why reinforcement learning comes into play and can actually help efficiently tackle this problem at runtime. So this is the solution we are proposing. It's basically my PhD thesis. It's called Figaro. We took letters from around the words just to make it sound nice. So basically it's divided into 2 parts. One is an offline training loop, and the other one is an online loop, meaning that the offline training is based on the fact that offline, we know what the expected behavior of a reinforcement learning agent is, while then we deploy it in a real environment. So basically we teach it how to behave in a scenario that we know, we fully know, because we, as I was saying, we know at design time how the agent is expected to behave when it's behaving best. And so basically we have a complex system with interactions between components, but the most important thing is the fact that we train a policy for this agent. So we basically teach the agent how to interact with the environment. Then we deploy it to a real environment with the same starting initial policy. And that environment is unknown because that's the online environment. Of course, it should be kind of similar to the one that we described at design time, of course. And so basically, for what concerns offline, the offline training, we see that, okay, this might not be the best plot, but basically we have the workload, which is red, and then we have the design time tool, which is the orange thing, and the blue is the agent, how the agent learns to behave. So it learns to mimic quite well the behavior of the design time expert. But when we deploy it online, we see the magic happening, because especially when we change what the system looks like to the eyes of the agent, differently from what it had learned in the offline phase, then we see that compared to any design time tool or any randomly initialized reinforcement learning agent, it behaves much, much better. Its response times are much lower, and it learns how to respond to fluctuations super efficiently. For what concerns how we implemented it, we have a hierarchical reinforcement learning system with an agent deployed on each computational layer, so that the complexity of the system that it needs to interact with does not explode. Since I'm running out of time, basically I'm jumping into developments, and right now we have implemented the solution for cloud virtual machines, but we are planning on extending the framework to edge devices, of course, which should be quite straightforward, while for function as a services it might be more tackling, but we will get there eventually. And then at the end we are going to test it on real environments, hopefully provided by industries. So I thank you for your time, and if you have questions, meet me later. Thanks.